I want to start this lecture by building on something that we discussed in the last lecture. We showed that if you have a field K that's generated over F by a finite set of elements alpha 1 up through alpha K, then we can understand K via a sequence of simple extensions. So we let our base field be F, we'll call that F0, and then F1 is F adjoin the first element alpha 1. So it's a field generated over F by alpha 1. And then F2 is going to be F1 adjoin alpha 2. So it's the field generated over F by alpha 1, that field adjoin alpha 2, and so on. So you get F0, F1 up through Fk, which is K, where Fi plus 1 is the field generated over Fi by alpha I plus 1. And we saw that in the case that alpha 1 up through alpha K are algebraic over F, my mistake, of degrees n1 up through nk, then because we know something about the degrees of simple extensions, we see by the multiplicativity of the degrees that the degree of K as a field extension of F is equal to the product of the degree of Fk over Fk minus 1 times the degree of F2 over F1 times the degree of F1 over F0. And if we know, for example, that alpha K is of degree nk over F, then alpha K satisfies a polynomial of degree at most nk over F. So it might satisfy a polynomial with coefficients in Fk minus 1 of smaller degree. So the degree over Fk minus 1 might be smaller than the degree over F, but we know it's at most nk. So we get this upper bound on each of these terms from the degree of the polynomial over F satisfied by alpha I, and that gives an overall upper bound on the degree of this field extension. Okay, so I want to come back to this. So that tells us a bound on the degree of this field extension, but how do we describe the elements of this field K, the field generated over F by alpha 1 up through alpha K? Well, what kind of an answer would we hope for? We know that if you take the field generated over F by alpha, the set of elements can be described as polynomials in alpha of degree at most n minus 1 with coefficients in F, where n is equal to the degree of this field extension. N is the degree of the minimal polynomial of alpha over F. Okay, so we would like to have something like this, but clearly now it's going to involve alpha 1 up through alpha K, not just a single element. So the second issue is we have this upper bound for the degree of K over F, but what is it really? Like if we want to look at a particular example, how do we decide whether this upper bound is correct, or how do we put in the right degree of this field extension? So I want to talk about these two examples, these two questions together. And I want to talk about the case K equals 2 for motivation. This contains all of the main ideas, and this is the same way this is presented in Dummett and Foote. So in this case, we can simplify the notation. We'll say that instead of having alpha 1 and alpha 2, we'll have two elements alpha and beta that are algebraic over F. So K is going to be the field generated over F by alpha and beta. And we're going to suppose that alpha has degree n over F, so the minimal polynomial of alpha over F has degree n, and beta has degree m over F. So what do the elements of the field generated by alpha and beta over F look like? Well, this lemma that we proved last time says that this field is the field generated by beta over F adjoin alpha. So for a field like this, we know what the elements look like. These are of the form polynomials in beta. Here, let me clear this up. Of degree at most d minus 1, where the coefficients lie in this field F adjoin alpha. And what is this d? D is the degree of the extension F adjoin alpha adjoin beta over F adjoin alpha. So that's our d. Okay, so we know that beta has degree m over F. What do we know about this d? So what do we know? We know that beta satisfies this polynomial, the minimal polynomial of beta over f of degree m. This is a monic irreducible polynomial with coefficients in f bracket x of degree m. And we know that if you take an extension of f, say the field f adjoint alpha, the minimal polynomial of beta over that extension, f adjoint alpha, has to divide the minimal polynomial of beta over f. Why? Because this minimal polynomial, this has coefficients in f bracket x. But since f is a subfield of f adjoint alpha, this also you can think of as a polynomial in f adjoint alpha bracket x that has beta as a root. So the minimal polynomial of beta over this field has to divide this polynomial. So what do we know? So this d, which is equal to the degree of the minimal polynomial of beta over this field f adjoint alpha, this thing, the degree here has to be at most the degree here. And the degree here is m. So what do we know about this d? We know that it's at most m. Okay, so I'm going to pause and erase. I'm going to talk a little more about this. And then we'll see how you can use this description of the elements of the field generated by alpha and beta over f to get a more concrete description of the elements, taking these coefficients in f adjoint alpha and rewriting them using the fact that we know what elements of f adjoint alpha look like. Our goal is to give a nice description of elements of the field generated by alpha and beta over f. And we've been talking about the minimal polynomial of beta over the extension f adjoint alpha. And we showed that the degree is at most m. It's at most the degree of the minimal polynomial of beta over f. But when is it actually equal to this upper bound m? So what needs to happen there is, well, you have this monic irreducible polynomial with coefficients in f adjoint alpha, and this other monic irreducible polynomial of degree m with coefficients in f, and this one has to divide this one. So they have the same degree if and only if they're equal. Okay, so when are they equal? That is, we have this irreducible polynomial, the minimal polynomial of beta over f in f bracket x. And if that polynomial is still irreducible, when you consider it as an element in f adjoint alpha bracket x, then these two minimal polynomials are the same. And in particular, their degrees are the same. So you could ask, okay, when does this happen? And this is really not so clear. So the point that I'm making is figuring out the degree of the extension f adjoint alpha and beta over the extension f adjoint alpha is not so easy if all you have at the start is the degree of beta over f. So this is kind of a subtle issue that's like not always obvious how to compute this thing. Okay, so leaving that aside for now, the fact that this degree is not always so easy to find, we can go back and take our description of the elements of the field generated by alpha and beta over f in terms of powers of beta. And by expanding out the coefficients, we get a description in terms of powers of alpha and beta. So we saw that we could describe these elements as polynomials of degree at most d minus 1 in beta, where the coefficients b0 up through bd minus 1 are in this field f adjoint alpha. So we know what elements in f adjoint alpha look like. And what does beta I look like? It's a polynomial in alpha of degree at most n minus 1, where the coefficients are in, these should all say a0i, a1i, all these coefficients a n minus 1i are all elements of f, where what is this n? It's the degree of f adjoint alpha over f. So by taking each one of these coefficients and writing it out as a polynomial in alpha, and now expanding, what do we get? We get elements of f adjoint alpha and beta over f being of the form this sum over I and j, where Okay, I is going to be the power of alpha. J is going to be the power of beta. I goes from 0 to n minus 1, the same n minus 1 here. And j goes from 0 to d minus 1, the degree of f adjoint alpha and beta over f adjoint alpha. And these aij's are just elements of the base field f. So this is our concrete description of what these elements look like. And you can think about how you would adapt this idea from the field generated over f by 2 elements to, say, the field generated over f by 3 elements. Now you'd have powers of each of those 3 elements, where you think of your extension in terms of a sequence of simple extensions, and the power that you go up to is the degree of each of those pieces. Like the degree of f adjoint alpha 1 over f is the first exponent for alpha 1. The degree of f adjoint alpha 1 and alpha 2 over f adjoint alpha 1 is the degree of the polynomial in alpha 2. And then the degree of f adjoint alpha 1, alpha 2, alpha 3 over f adjoint alpha 1 and alpha 2 gives the power, the degree of the third alpha 3. Okay, so what do we know? We know that the degree of this extension is the product of the degree of f adjoint alpha and beta over f adjoint alpha, which we know is d. That's the degree of this minimal polynomial of beta over f adjoint alpha. And we know that times by multiplicativity, we have times the degree of f adjoint alpha over f. We know that that has degree n. So this whole extension has degree d times n. So what have we seen? We've seen that every element in this field can be written as an f linear combination, as a linear combination with coefficients in f of a bunch of special elements, that is alpha I times beta to the j, alpha to the I times beta to the j, where I goes from 0 to n minus 1, and j goes from 0 to d minus 1. So what are we seeing? We're seeing that this set of d times n special elements are a basis for this field generated by alpha and beta over f as a vector space over f. And again, you can think about how this changes when you go from the field generated by 2 elements to more than 2 elements, where you get a statement that's very, very similar. So I'm going to pause and erase, and then we'll talk about some basic examples of computations with these kinds of field extensions. Let's look at the example of the field generated over Q by the 6th root of 2. We'll use this symbol to mean the positive real number that you raise it to the 6th power and you get 2, and the square root of 2, the positive real number that you square it and you get 2. Okay, well, this field is generated over f by alpha and beta, so it is the field generated over f adjoint alpha by beta. So this is Q adjoin the 6th root of 2 adjoin the square root of 2. But this just is Q adjoin the 6th root of 2 because square root of 2 is already in this field, Q adjoin 6th root of 2. Why? Because square root of 2 is the 6th root of 2 cubed, which is clearly in Q adjoin the 6th root of 2. So what does that tell us about degrees? The degree of this extension over Q is the product of the degree of Q adjoin 6th root of 2 and square root of 2 over Q adjoin 6th root of 2 times Q adjoin 6th root of 2 over Q. So this first extension has degree 1 because these two fields are the same. And then this extension has degree 6 because the minimal polynomial of the 6th root of 2 is x to the 6th minus 2, which is irreducible in Q bracket x. So 1 times 6 equals 6. But one thing that we haven't really discussed yet is that there is some totally arbitrary choice when you think about the field generated over f by alpha and beta as being the field generated over f adjoint alpha by beta. Like, there's no clear choice which one should be alpha and which one should be beta. So it's true that this field is also the same as the field generated by the 6th root of 2 over Q adjoin the square root of 2. So if you go the other way, you see that this degree, which we know is 6, is equal to the product of the degree of q adjoin the sixth root of 2 and square root of 2 over q adjoin square root of 2 times the degree of q adjoin square root of 2 over q. This we know is 2, which means the degree of this extension must be 3. Okay, because 6 has to be something times 2, so it must be 3. So let's think about what that means. That's saying that the minimal polynomial of the sixth root of 2 over q adjoin square root of 2 has to be degree 3. So let's find some monic polynomial satisfied by sixth root of 2 with coefficients in q adjoin square root of 2. Well, here's 1, x cubed minus the square root of 2. This is a polynomial in q adjoin square root of 2 bracket x. So it has to be divisible by the minimal polynomial of the sixth root of 2. But since the degree of this extension must be 3, this has to be the minimal polynomial, because the minimal polynomial has to have degree 3. So one thing this tells you is that this polynomial is irreducible in q adjoin square root of 2 bracket x, which is not at all obvious to me. So if you think about this field in two different ways, like switching which element is alpha and which element is beta, it tells you different things. So if we take the description of the elements of f adjoin alpha and beta, you'll also see that that description depends on which element you think of as alpha and which element you think of as beta. So in this example, what happens? We have q adjoin sixth root of 2 and square root of 2 over q. What we get are polynomials in these two elements, where in the first case, we have the degree of the square root of 2 is the degree of this extension, this relative extension, the whole thing over q adjoin sixth root of 2, which is degree 1. So this is polynomials of degree at most 1 minus 1, which is 0. And then the degree of your first element, alpha, is n minus 1, where n is the degree of this q adjoin f adjoin alpha over f extension. So what we get is polynomials with coefficients in q of degree at most 5 in sixth root of 2 and degree at most 0 in square root of 2. But okay, degree at most 0, that means you're just getting square root of 2 to the 0, just 1. Really, what are you getting? You're getting the description of polynomials of degree at most 5 with coefficients in q in this one element, sixth root of 2. And that makes sense because that is the description we have of elements of q adjoin sixth root of 2. But if you think about it this way, go the other way, what description do you get? You get polynomials with coefficients in q of degree at most 1, 2 minus 1 in square root of 2, and degree at most d minus 1, where d is the degree of this extension here in sixth root of 2. So we get aij times square root of 2 to the I, where I can be 0 or 1, times sixth root of 2 to the j, where j can be 0, 1, or 2. And okay, this doesn't look exactly like this, but these fields are the same, so they have to have the same elements. So the one other thing you have to do to just see that these really are the same is note that, okay, this I could be 0, in which case you get the first 3 powers of sixth root of 2. But if this I is 1, what is square root of 2 times sixth root of 2 to the j? It is sixth root of 2 to the j plus 3. So that's where you get the other 3 powers. So these descriptions are the same, but maybe not obviously so. So I think this example, while being a little simple because this element square root of 2 is in the field generated by sixth root of 2 over q, so that this really is a simple extension. This already is showing that it's important that there's a real choice to be made about the order when you're taking the field generated by more than one element. Okay, so I'm going to pause and erase, and I'll talk about another example. Let's next consider the field generated by square root of 2 and square root of 3 over q, where again, we mean the positive real number that squares to 2 and the positive real number that squares to 3. So each one of these is algebraic over q. The minimal polynomials over q are easy to write down, x squared minus 2 and x squared minus 3. So what is the degree of this extension over Q? Well, it is the degree of the extension Q adjoins square root of 2 and square root of 3 over Q adjoins square root of 2 times the degree of Q adjoins square root of 2 over Q, which we know is 2. So this has degree 2. This has degree at most 2 because it's at most the degree of the minimal polynomial of square root of 3 over Q. But maybe it's actually smaller. So we see that this extension has degree at most 4. It could be 4, but it could be 2. So how do we know which one it is? So that's the same question as asking what is the degree of this extension, which is asking what is the degree of the minimal polynomial of square root of 3 over Q adjoins square root of 2. So we know that there's one polynomial with coefficients in Q adjoins square root of 2 bracket x that it satisfies, x squared minus 3. So the question is that the minimal polynomial? Or is the minimal polynomial actually degree 1? So that's asking, is x squared minus 3 irreducible in Q adjoins square root of 2 bracket x? And we know that this is irreducible if and only if it doesn't have a root in this field. We know what the roots are in the real numbers. It's plus or minus square root of 3. So if it has one root, it has both. That's just asking, is square root of 3 in this field Q adjoins square root of 2? Yes or no? So answering this question will answer all of these questions and determine whether the degree of this extension is 4 or 2. Okay, well, how are we going to answer this question? The answer is no, but it's not obvious that it's no. We know what elements in Q adjoins square root of 2 look like. They're polynomials with coefficients in Q of degree at most 1 in square root of 2. So every element is of the form a plus b times square root of 2, where a and b are rational numbers. So if square root of 3 was equal to a plus b square root of 2, where a and b were rational numbers, we could square both sides and see that 3 would be equal to a squared plus 2b squared plus 2ab square root of 2. Okay, this looks like a problem because, so this looks like a problem. If a times b is not 0, then 2ab is not 0, and we can solve for square root of 2 in terms of a and b. I mean, more specifically, square root of 2 equals 3 minus whatever this is, a squared plus 2b squared over 2ab. The right-hand side is a rational number, and we know that square root of 2 is not a rational number. That's an argument that we have seen before at this point. So this is a contradiction. So if there are rational numbers a and b that make this true, certainly a times b equals 0. So we'll just deal with the case a equals 0 and b equals 0 separately. If b equals 0, then we get square root of 3 equals a in Q. And the right-hand side is in Q. The left-hand side is not. So that's also a contradiction for the same reason. And we know square root of 2 is not rational. Square root of 3 is not rational. So if a equals 0, what does that tell us? Square root of 3 equals b times square root of 2. We can multiply both sides by the real number square root of 2. We get that the square root of 6 is equal to 2 times b. And 2 times b is a rational number, but the square root of 6 is not. So this is also a contradiction. So we've shown in a very hands-on brute force kind of way that square root of 3 is not in this field Q adjoins square root of 2, because we have a good description of what the elements of this field look like. Okay, so what does that tell us? So square root of 3 is not in this field, which means that x squared minus 3 is irreducible in Q adjoins square root of 2 bracket x, which means that the minimal polynomial of square root of 3 over Q adjoins square root of 2 has degree 2. So this field extension has degree 2, and so the original field extension was an extension of Q of degree 4. Okay, so I'll pause and erase and say a little bit more about this example. Given our discussion of this field generated by square root of 2 and square root of 3 over Q, we get a nice description now of the elements of this field. It's polynomials with coefficients in Q of degree at most 1 in square root of 2 and degree at most 1 in square root of 3. So that's a plus b times square root of 2 plus c times square root of 3 plus d times square root of 2 times square root of 3, which is square root of 6, where a, b, c, and d are elements of Q. So this is our nice description of what the elements of this field look like. So in particular, we have this nice basis for this field as a vector space over Q. All right, so I wanted to mention an exercise that's on homework 3. This is exercise 7 in section 13.2. You could say, like, okay, this is one description of this field, but is there another, maybe better or different one? And you show that this field generated by these two elements, square root of 2 and square root of 3, in fact, is a simple extension of Q. It's generated by the single element square root of 2 plus square root of 3. And the idea is you can show containment each way. I'll leave that to you to think about. But if you believe that this is true, we've shown that this extension on the left has degree 4 over Q. So that means that this element, square root of 2 plus square root of 3, satisfies an irreducible harmonic polynomial of degree 4 in Q bracket x. So what is it? Like, how do you find what that is? And there's a neat idea here that once you see it, you'll know how to answer these kinds of questions. In general, I'll do a slightly different example. Instead of using square root of 2 plus square root of 3, I'll say square root of 2 plus square root of 5. What happens when you square this? What you get is 2 plus 5 plus the cross terms, which is 2 times square root of 2 times square root of 5, which is square root of 10. Okay, so we still have a square root in here. But the idea is if we move the 2 plus 5 over to the left side, now we have something on the right side where if we square it, we're going to get a rational number. So what's the idea? Square root of 2 plus square root of 5 squared minus 2 plus 5, which is 7. That's equal to 2 times square root of 10. So if we square it, we get 2 times square root of 10 squared, which is 4 times square root of 10 squared, which is 10, which is 40. That's some rational number. But what happens when you square this thing? Just multiply it out. You get square root of 2 plus square root of 5 to the 4th minus 2 times the cross terms, which is minus 14 square root of 2 plus square root of 5 squared plus negative 7 squared, which is 49. Okay, so now you can subtract the 40 from the 49, and you see that square root of 2 plus square root of 5 satisfies a polynomial of degree 4 with coefficients in Q.